I'm Chris Major. I'm a research assistant at Montana State University. I'm in the electrical and computer engineering department. I'm also the principal engineer for Resilient Computing, which is our student-built commercial spinoff of the technology I'll be talking about today. And today I'll be discussing intrusion-tolerant flight computing through hardware obfuscation. It's a project that we call CyberShield. It's been funded through Raytheon, one of their university research programs. And without further ado, I'll kick into we'll start with an overview of just different concerns of cybersecurity and the one that we decided to focus on specifically for our research. So you can see here we have 6 different types of attacks, many of which have already been previously discussed. We've talked a lot about malware so far. We also have more social aspects such as, say, phishing or password attacks, in which there's very much a present human element to that. Denial of service attacks are a big one, especially for anything on a network or dealing with servers. Man in the middle and drive-by downloads being 2 other networking concerns. But the one I want to focus on today is specifically malware, which we can define as inserting malicious code into a computer's program memory and then tricking the processor into running it. And one of the ways this is commonly done is by trying to take computer data or values in your data memory and trying to get them to look like values you'd see in your program memory. And so suddenly data turns into instructions, and now we have the system being compromised. But before we go further, let's just talk about the main challenge that takes place within malware. And this has kind of been discussed in the previous presentation regarding the various different components and vehicles. So one of the biggest advantages for programmers and developers is that for the most part, there's a lot of parity between hardware. We call it homogeneous computer systems. A lot of computer systems are identical in their form and function, and so it is easy to take a program on one system and easily move it over to another, especially in, say, like a server or a data center. And this comes in easy for developers and programmers, because if your program works on one system, the odds are very high you can take that program, put it on the rest of the systems, and reduce your work. So this concept is homogeneity, and this is the best possible scenario for, well, software development. Unfortunately, it is also the best possible scenario for malware and for malicious agents. This gives an advantage to a hacker because your effort to try and develop malware for a specific system is far easier, because if you can get on one system, you can get on multiple different systems since you already understand the entire architecture. Now, let's take a step back and think about systems and computers. So in 2018, for instance, 400 million personal computers were sold, such as laptops, desktops, gaming rigs, etc. But then dwarfed by that is the smartphone market. 1.5 billion of these were sold in 2018, and these days they're ubiquitous. There are very few things that you can do without a smartphone these days. But what if I told you that there was an even bigger market, and dare I say, an even more susceptible market? This would be the embedded computing market. So now we're no longer looking at just your standard PC or your standard smartphone, but embedded computers in everything. Vehicles, as we discussed earlier. Different sorts of entertainment systems, your Xbox, PlayStation, Switch, nothing but embedded systems. Even basic office supplies, printers, routers, modems, etc. Use embedded systems. And especially of more concern these days as the market keeps rapidly expanding, the Internet of Things, which is basically just fancy marketing lingo for lots of embedded systems all on a Wi-Fi. Is there security? Possibly. So our research focuses on diversifying embedded computers. And we'll talk a little bit more about what that specific term diversifying means in just a second. But first, let's go and just kind of zero in on a definition of what an embedded system looks like. Now, granted, it's not a one-size-fits-all for many devices, but typically embedded systems have smaller physical dimensions. You can even get down to, say, small little 8-bit ICs that can fit on the end of your thumb. You have lower clock frequencies, about 1 megahertz to 16 megahertz. You generally have smaller memory devices attached to it, often small NAND chips, sometimes removable storage, but for the most part, most embedded systems are able to run well below a megabyte of storage space for programming data. Now, embedded systems have dedicated software for dedicated uses. They're not generally general purpose. and often they don't have an OS, maybe just a real-time scheduler at best. Now, granted, there are devices like, say, the Raspberry Pi that kind of blur these lines a little bit. But for the most part, embedded systems have all of these qualities that across their entire product families make them very much homogeneous. In a sense, for instance, if you attack one Arduino, you could attack a lot of other Arduinos because you already know what's there. All right, let's go to the next slide here. So if homogeneity is a problem, even given its advantages for development, if homogeneity gives too much advantage to attackers and malicious agents, well, it seems logical the best way to go about trying to reduce the ease of malware would be to diversify the network and randomize the hardware. So in a sense, we want to go ahead and try and remove the homogeneity. This would be a technique that we call obfuscation. The idea being that, okay, maybe the structure or system that we have here is known to some degree, but the more elements of it that we can obfuscate or make it difficult to understand, the better, and the less the attacker has to work with. Sort of, you don't know what you don't know until you don't know it. The problem with hardware is that computer hardware is fixed and it takes months, if not years, to fabricate. So taking anything from a basic circuit design all the way to a VLSI design and then getting it sent to fabrication for manufacturing, it's a long and lengthy process, and it's very permanent. Once an IC is built, that's the way it's built. It's not changing ever. However, there has been a lot of work in the areas of virtual machines, be it in a software environment or in some cases even a hardware environment, where now the architecture of a computer system is variable enough that we can introduce changes. And one of these changes comes down to the idea of instructions. If you could randomize the instructions in a computing system, the attacker doesn't necessarily know what's there or what they have to work with. It's now trying to inject malware becomes more difficult because you don't exactly know what resources you have to strike at. So one such technology that would allow for trying to create new types of hardware where we have flexibility in obfuscation is a field programmable gate array, or an FPGA. So FPGAs, just for those who are unaware, are digital logic devices that can be configured into any sort of computational architecture. So imagine like a large logic matrix with just literal millions upon millions of logic blocks. And depending on how you go ahead and reconfigure those blocks, you can create any sort of logic circuit possible. You could create a processor, you could create a digital audio converter, you could create like a small network cluster of processors. But the point being that an FPGA in the developer's hands is reconfigurable. So custom hardware can be built and executed on this device to solve a problem. Now, FPGAs can take advantage of parallelism and redundancy for hardware acceleration. What this means is that creating one component on an FPGA means you can, in many cases, quite literally, copy paste that component over and over again, and make modifications to that component with certain parameters. So FPGA design is incredibly modular, and if done right, is incredibly parameterized. Now, the best part about FPGAs, especially in a day and age where we're still trying to recover from supply chain issues within silicon, is that FPGAs are widely commercially available and are only growing in their commercial footprint. Now, the extensive development and support makes it really easy to take an FPGA device and get developing on it, given you have the tool from the ecosystem. And often those tools are free and well supported. So FPGA hardware is designed using what's called a hardware description language, or an HDL. Now, this is different from, say, a standard programming language where, in essence, you're staging a sequence of operations to be followed. So instead of trying to program sequentially, an HDL forces you to program everything in parallel. So you're describing physical digital hardware with an HDL. And once this HDL is created and simulated, you can then go ahead and use scripts to create different versions. So we're going back to those modules, that sort of parameterization. Now, the best part is that the HDL can be created at compile time. So you may roughly know what a design should operate like, and you can define your parameters, but the tool will define what it actually looks like on the physical device at compile time within your FPGA suite. And this will come in handy a little bit more when we explain specifically more of the tool chain. Now, this HDL, when it becomes an actual design on the FPGA, we refer to it as real-time logic, or RTL. So RTL is like the physical description of all the logic blocks on the FPGA. This involves the placement, timing, the sort of things that you would send to a manufacturer if you were building a standard microchip. Now, the RTL is generated through the FPGA vendor synthesis and implementation suite. So basically, imagine your compiler software provided by Intel Altera, AMD Xilinx, Lattice, etc., one of those companies. They hand you the software package and they say, hey, just throw in your HDL. We got a couple of custom scripts for you. We'll go ahead and we'll handle the process of putting it on the FPGA. And as an end result of that process, you now have a bit stream. So we take our custom hardware on the bit stream and we throw it onto an FPGA. But the benefit that we want to exploit here in order to work on this idea of homogeneous versus heterogeneous cores is to take advantage of this modularity and this parameterization. So imagine, for instance, a computer system that we've designed in VHDL. We've gone ahead and we've created one computer core. But because we can parameterize it, let's create two more. So you can kind of see, hopefully my mouse is showing up. If not, we have 3 computer cores here that we created with our hardware description language. We're going to feed them into our tools for synthesis and implementation. And the result's going to be this physical computer chip that we can work with. So what does our baseline computer look like? Well, let's say for the example of trying to anticipate malware, that we have our original processor design, so it's not locked behind proprietary contracts, NDAs, etc. Let's say it's open source and that the opcodes are known. So an attacker could go onto GitHub and look at the opcodes and figure out, okay, this instruction means this instruction means this, here's what the architecture looks like. And on top of that, we've now given compiler support as well. So now someone could download the compiler tool and put together a binary in C that would then be able to be injected into the core. And the thing is, this might sound a little bit artificial, but if you think about a lot of processors that currently exist out there, especially ones in, say, the RISC-V ecosystem, this is very much the case. And if we were to think about, say, a corporate environment, even if your technology is proprietary to the outside world, an internal employee still has access to most of these elements. So for this example, let's just accept this risk that this processor is well known. But because we're in an HDL, because we have those parameters on our modules, let's create 2 more of these computers, but we're going to vary the instruction opcodes before synthesis. So what we're going to do is we're going to tell the synthesis and implementation tool, hey, by the way, we want you to shuffle around these opcodes. We don't know specifically what they're going to look like, but go ahead and shuffle them around. The hardware will know what instructions it has, but we won't know. We'll only know one of these core's instructions. So what we then have is it's functionally equivalent, but now they're heterogeneous cores. So one of these cores we know well, we can look it up. There's GitHub. There's probably a few Stack Overflow pages complaining about certain features, as with any processor. But these other 2 processors we really don't know anything about because the tool has done all the hard work of creating these different instruction opcodes. And so now we have a bit of obfuscation in our heterogeneous cores. So now let's say our malware has attacked. We have a bad agent that has come in through one of our input ports, let's say a UART, a SPI, etc., and they managed to inject malware onto the core. It's like a buffer overflow attack. So now as you can see here, all 3 of these cores have the exact same malware because they're now sharing their input ports and output ports. All 3 cores have technically been attacked, but only one of these cores is actually going to fall through on the malware because these are the instructions that are publicly known and publicly recognized by the microcontroller. So this one right here is going to suffer from the hack. These cores, however, because we randomize the opcodes through the synthesis and implementation process, they don't recognize the malware. For them, it's foreign opcodes that just don't make any sense. And so now we have a couple scenarios we can do. We can throw an exception so the cores can report back and say, hey, I don't recognize this instruction. I'm not going to run this. Or we can have a system in place so that when one of the cores comes across an instruction and it's saying, I don't know what to do, I don't recognize this, that's fine. We have a mitigation strategy then in place to go ahead and remove that malware now that we know that this opcode is not acceptable in the system. So this is the kind of the bread and butter of our CyberShield concept. We call it a compile time creation of obfuscating computer hardware. And just for a little audience engagement, how many of you have played with any sort of microcontroller suite, like Code Composer Studio, maybe Android Studio? Okay, I'm seeing a few hands. Okay, so then you know this process where you create your C files, main.c, maybe your libraries. You're now developing software on an embedded system. And so with any similar tool chain, you usually combine that with some sort of environment file. So with Arduino, you specify the kind of Arduino you're playing with, and so they give you an H file for that. Or in Code Composer Studio, you have to select a deliberate MSP 430, for instance. Or if you're doing, say, platform I/O, you bring in your configuration files so that way it knows what microcontroller you're targeting. And so now you have a proper file with your main.c, you have your library files, and on top of that, you have your runtime startup. So one of the things that C programs require is some sort of environmental tool or a quick set of instructions that basically tell the core, hey, by the way, you're going to run this main.c, and here's how you're going to do it. Because a computer isn't just going to jump right into main.c. It needs to know how to set up the environment. And so when we have that in our tool set here, we can run it through a compiler, like GCC, for instance, or Clang if you're one of the cool kids, not going to lie. Then you get yourself an executable file, or an executable linker file, more specifically. So we're going to call this main.o. And then your main.o is basically just a binary string of all your opcodes and operands. And so if you have a custom script that can shove that into your VHDL, now you have this singular core right here, our CyberShield Core 0. So this process seems pretty simple compared to most microcontrollers, pretty routine. But what if our attacker gets us our instruction codes? Because again, we're going to run with the assumption that it is possible to find out these codes. Well, now what if we have two sets of different instruction assignments within this tool chain? So now the tool chain, when it gets our binary, it says, hey, I'm going to create this one core in the HDL, but I'm also going to create a second core with instructions that are obfuscated. They're different. The core will be able to understand it, but it's going to be translating it to itself, and we on the outside don't know what those opcodes look like. Well, now, again, if we get the malware and we compare the two sets of opcodes that are injected in the malware, you have one malware stream, but two sets of opcodes. And so one of these is going to affect the core, and the other one's going to make no sense to the core. But why stop at two? We can add multiple sets of instruction codes. In fact, if we have enough instruction codes, enough cores working off of enough instruction codes, now we can start looking at the idea of like a majority. Because if one core is being affected by malware and it's starting to act weird, but the other cores are fine, well, now we have a clear majority of 3-1. And so now we can start trying to diagnose where it actually happened in hardware and figure out which cores need to be repaired and which cores need to keep going. But why add more than two computing cores in the first place? I mean, it should be pretty easy to tell if one's acting weird and the other's actually following its program, right? Well, this is a concept that actually goes over to flight computing component. And I promise that even if this next part does sound like a bit like a tangent, we're going to pull it right back around. Because there's actually a lot of similarities between aerospace and cybersecurity within defense. In fact, a lot of principles that are used in this research for defending multiple processing cores with redundancy mechanisms and voting mechanisms are actually techniques used in the aerospace industry. In fact, MSU has a history of building and deploying various space computers. We have a platform known as RADPC that has been developed in the lab. And this platform basically takes the reconfigurable logic, so like an FPGA, and redundancy mechanisms, like those multiple cores that we just discussed, to protect program execution from radiation faults. In fact, we've demonstrated this technology since about 2010 with multiple experiments going up into space and demonstrating what we call flight heritage. We've done about 8 HAL-2 balloons, 2 sounding rockets, 3 International Space Station missions, 2 CubeSat satellites, and 1 upcoming lunar mission. And one thing that the aerospace industry loves as much as the defense industry is flight heritage, which is your confidence in implementing the hardware and software onto many missions. So the more it's been used, the more these industries like this technology because they know that the probability of it working again is pretty high. But let's wrap this back around for a second. What is the connection between space radiation and malware? Well, if you think about it, there's actually quite a lot of overlap between the two problems. For instance, both space radiation and malware result in unexpected error injection into the system. So if a radioactive particle strikes your memory in space and corrupts a data value, that's pretty similar to how malware will basically rewrite a data value in memory at an unexpected time. You certainly don't schedule malware attacks, or at least schedule when you want to defend malware attacks, and you certainly don't schedule cosmic radiation. It also results in manipulation of program data. So where a malware injection can certainly strike into your program memory and change what is going to happen with your next instruction, it's also very much possible with space radiation to have your program memory hit by a random cosmic particle, and suddenly you're out in the weeds in terms of your program execution. And on top of that, a lot of research focuses on mitigating both space radiation and malware through redundancy. So how can we leverage the RADPC fault recovery mechanisms in our little cybersecurity application here? How can we kind of marry these two worlds to get the best possible scenario? Well, funny enough, we're kind of doing that in our workflow already. We just need to define a little bit more what that looks like. Now, RADPC has something called a quad modular redundancy system, or QMR, which is a standard that we created from RADPC that generates 4 different processing cores. So all 4 of these cores here basically act like a majority voting system, but with the ability to swap out a core if it's damaged and keep the majority voting alive while it's being repaired. Now, in this workflow, we already ensure that each core can only understand its own opcodes. So all 4 of these processors are separate from each other. And this makes sure that if malware is injected onto one core, the other cores cannot recognize it. And the other cores don't know what the other opcodes could be, thus limiting their ability for them to realize, oh, actually, this malware, we can run that. If we also add like a voting mechanism, now, as mentioned earlier, now we can use a majority advantage of these cores to identify where a core has been attacked. So again, if core 0 goes down, the other 3 cores are running. Those other 3 cores must be doing something right if they're all in the majority. And if the thing that they're doing right now is looking at this opcode going, I don't understand this, then the odds are really, really high that core 0 has a faulty opcode and we're possibly dealing with some malware. And on top of that, if we add a recovery mechanism, now we can bring that bring that processor back online. So we can refresh the program memory, we can reset the program counter, bring it to a known instruction and keep going from there. But at least we have some means of pulling back from the cyber attack and moving on beyond, oh, I don't understand this opcode. What's going on? So one of our first demonstrations to run with this concept was to create a FPGA version of a microcontroller, run it against a standard commercial microcontroller, and kind of create a sort of simulation of what it would look like in a real cybersecurity need. So this was the beginning of our research with Raytheon, and we created this demo here where we had these 2 3D printed like missiles. And the idea being that this missile has an angle it should be at, and it means of controlling that angle to keep it consistent. So imagine if you pushed over one of these missiles right here, we have the stepper motor that will pull it back into place, and we have this angle sensor, the angle sensor and stepper motor on both of these, by the way, which would then make sure that the missile was brought back to the correct angle. And we have our 2 microcontrollers. So we have this FPGA here with our VHDL microcontroller. This has the whole redundancy mechanisms, opcodes, etc. And then we just have the standard Texas Instruments MSP launchpad controlling the other rocket. And finally, to introduce our attack vector, or the place in which malware can be injected, we have a UART that is fed into both of these. And all the UART does is specify the angle to bring the rocket to manually. So let's go over what it looks like in the memory map for this sort of attack. So with the UART here, we want to do a classic buffer overflow. Quick show of hands, just for the heck of it. How many of you are familiar with a buffer overflow or have performed one? Okay, so you guys know what's up. I'll go over just a really quick then. I won't take up too much time. I want to leave some time for questions. But in this example here, let's say we have our data memory right here. So we have our frequency and our set angle, which correspond to the motor controls. And then here we have other values within a data memory, such as our receiving index. We're going to receive a variety of characters on our UART buffer. And on top of that, we're going to have our local variables growing on the stack as we go forward. At the very end, we have our ISR return address, so our instruction return. And this one is incredibly important because this value in data memory directly ties to where we're going to go back to in our instruction memory. So imagine this is our hacker's packet. Our hacker wants to take advantage of the fact that our angle is set over UART and inject a little NOP sled here. So you put in a bunch of NOP values for those who had performed this sort of attack. And those NOP values basically clear out your data memory up until you reach a point of malware. And so now these are your actual instructions you want to use to affect the system. Perhaps on this rocket, you want to set the correct angle, or you want to turn the thing off. Or maybe just want to catch it in an infinite loop and freeze it up. Whatever your heart desires, you put it right here in the malware. Add some more NOP sleds just to clear out anything that could be important in your data memory. And then by the time you've gotten to where you expect the ISR to be, because keep in mind, you know what this architecture looks like, you can now put in a new instruction return address. And if this new instruction return address goes back into your NOP sled, you will perpetually keep the system in your little bit of malware forever. And all this can be done because we have our UART connection that is going into the system, and where our UART expects you to put in an angle and then wait to see if you put in anything else before returning, we have a vulnerability where our buffer overflow says, our buffer says, hey, I have a value, I'm going to store this. Oh, you're giving me another value? Okay. Oh, another one? Okay. And as it's fetching new values from the UART, it doesn't realize that the interrupt timer on it hasn't quite yet clocked out. And so we abuse the timing of this interrupt on the UART, not just to feed in one value for the angle, but to feed in another value and another value and another value. And now our data memory is completely taken up by our NOP sled and our malware, which in the end allows the attacker to put in their own program into data memory and then trick the processor into running it by having the instruction return address feed back into data memory. As you can imagine, this crashes the system. In the case of the missiles, would then go ahead and cause their angle to turn off entirely. The stepper motor is no longer controlling it. The angle sensor has completely lost any readings, and now the system is compromised. But if we use our system, again, this previous one, assuming that we just have a standard microcontroller, if we bring in the CyberShield system, we technically have 4 CPUs worth of memory that we're attacking. And so where CPU 0 here might recognize that these are no-ops. This is executable code, and this is a return address. These other cores have absolutely no idea whatsoever what this even means. In fact, in this case, where this might just be regular data for any other microcontroller, here, these are all foreign opcodes. It cannot recognize any of these instructions. And so if CPU 0 is compromised, it's the only one that can actually run the malware. The other cores simply will not run the instructions because they do not understand them. But what kind of processor can we use for this strategy? Will this be applicable to really any sort of computing system? The answer is yes and no. So in our example in the rocket demo, we used an MSP430. So this is a launchpad board we use a lot here at MSU for microcontroller projects and classes. It's 16-bit, provided by Texas Instruments, and it's a large, extensive, and well-documented family of microcontrollers. Because of that, the opcodes are widely available. Everything's public. You can go on the site and check it out. Granted, you don't have the proprietary knowledge of the internals, but again, for malware, all you really need to know is what the architecture looks like and what opcodes you need to manipulate that architecture. Unfortunately, that does put us at a disadvantage because trying to recreate the entire MSP430 but on an FPGA proved to be fairly difficult. And we got close enough with this demo to basically mimic the functionality. But there are no open source softcore versions of this microcontroller that we could put onto an FPGA and add in our internal signals to identify when a bad opcode requires a recovery. So we decided we're going to move from this black box processor, where basically we can't have access to the internals, and we're going to go ahead and use like a glass box processor. So quick show of hands, how many of you guys have heard of RISC-V? Honestly, that's more hands than I expected, but I'm totally fine with that. RISC-V is awesome. So it's an open source industry standard architecture for those who may be unaware, created by UC Berkeley. And basically, this is an entirely 100% open source processor architecture design. You could go onto the RISC-V website shortly after this presentation, or probably more accurately after the workshop. You could read through the documentation, and you can create your own RISC-V processor. You could put on FPGA, you could simulate it on your computer in a virtual box. If you felt so inclined, you could build an ASIC from scratch off this. Why you would do that, I don't know. But the point being, everything about the RISC-V is open source. The base form is a 32-bit integer-based core, which we use for our research. And we can easily put this onto an FPGA by either picking one that's already open source or handwriting our own that we can go ahead and manipulate. And as long as the design conforms to the ISA through a series of checks and a series of checks and checklists, you can go ahead and assume full RISC-V functionality. And you can run a C program off of it, for instance. So we got ahead and we created our own RISC-V to try and replace the core that we created for the last demo. So we have a RISC-V RV32i, and this is just the RISC-V core, 32-bit values, integer operations only. That's what the RV32i means. We did this all in VHDL components. We have about 4 kilobytes of instruction memory, or IMEM, and about 4 kilobytes of data memory, or DMEM, which is plenty enough to build a pretty decent sled. But we also added some GPIO to try and interface with another sort of interactive demo. So we added 2 GPIO to it, 2 UART ports, 2 SPI ports, and all these are accessible. Now, again, we're trying to maintain the assumption that our core is known. We're not going to try and make up a core that would be difficult for a developer to program. We're just going to go ahead and assume that, all right, people are going to know the base opcodes for our core because it's the RISC-V. But this at least gives us the advantage of easy development and easy maintenance. And one of the best things about RISC-V is that the compiler is free, open source, and runs pretty well. So we can create a custom makefile that will compile all of our C programs into binaries, and then we added a Python script that can export those binaries into the HDL components. Now, right now, minimal library support is added. Standard I/O is a way out because the thing's a monster, but at the very least, we can do basic integer-based operations with standard int. So now we went ahead and created a demo of some sort. So the Rocket demo worked fine, but we had a couple other grants in lab, and we were trying to figure out how to overlap different ideas. And one idea we had was, let's keep the idea of an input sensor of some sort and an output result of another sort. But we decided to mix it up a little bit and bring in camera image data as our input, and then have our screen as an output. So we created a system which would be able to take in raw image data from a basic camera, one of the OV modules, and then output that data to a screen. And then for our attack vector, we figured, let's go ahead and have a UART come in again, just as we did before, but we're going to do a basic operation on the image that's easily visible on the screen. And so we elected to do a basic edge detection, just a quick horizontal edge detection. So the idea here being that we have a system that's taking in sensor data, outputting it, and we have the perfect attack vector where someone could either flip the mode of the screen or perform a buffer overflow. So this was all done with the RISC-V architecture. So now we've replaced our MSP430 clone on the FPGA, and we've inserted our own RISC-V core. And this has the hooks necessary to detect an illegal opcode and alert our correction mechanism to go ahead and refresh that program memory area. And our UART is still present in the system. It goes to all 4 cores. They're sharing the same UART. And this specifies whether or not we want our regular screen or if we want the edge detected version. So again, going back to our vocabulary for malware, this is our attack vector. Now, again, each of these processor cores has the different opcodes, but the same input ports, output ports for the entire system are shared. So I'm going to go ahead and show you a demonstration video. This was done by one of our graduate students, Tristan Running Crane. He actually passed his defense with this, which is pretty nice. I'm going to go ahead and switch the screen for a second because it's a YouTube video. Okay, let me share screen. Project demo. Okay, and just to double check, you all can see this?
Yes, we can.
Okay, enthusiastic thumbs up. Thank you. All right, thankfully it doesn't have any audio, so I don't need to worry about that. But I'm going to go and play through this clip a little bit, and I'll kind of pause and explain what's going on. But first off, we have our camera set up here. So this is our camera feeding into our new system. So this uses the RISC-V cores, same Cyber Shield, but 4 different RISC-V cores that have been programmed with a C program. All of them have their different opcodes, pretty much everything that we talked about. We have our little display screen right down here with the MSU logo, Go Cats. And on top of that, we have this wire here is going over to Tristan's computer at his desk. So he's going to perform the attack off of that computer just over UART. So here we go. Let me restart this. There we are. Okay, so you can see in this little window down here, let me see if I can get this to be a little bit more quality. We don't exactly need 4K, but it'd be nice to be able to read it. There we go. So we have a basic Python program just using Python serial library. What this is going to do is it's going to send in a ton of bits and take advantage of the fact that the interrupts on the UART are firing off way too quickly. We're sending in way too many bits, and our UART is designed to just take in as much as possible for the UART and then process it from there. This is pretty standard across a lot of microcontrollers. It is not best practice, but unfortunately it's been adopted in so many systems that it's considered fair game for a demonstration like this. So as you can see here, we have all these values that we're just going to shove into the UART. We go ahead and we hit run debug. And now as you can see here, we have this logic analyzer up top. Now you see how the screen just crashed right there? So that corresponds to this little window of time right here. We have an internal logic analyzer in the FPGA that shows all these opcodes firing off on all 4 of the processor cores. And these little gaps up here indicate that the a recovery mechanism is watching the cores and being like, okay, everything's fine. They're not reporting any weird opcodes. But then the minute we hit this window here, which corresponds to right when the screen started acting up, we notice that we have illegal opcodes in the system. And because we know they're illegal, because they're the same 4 opcodes across all 4 tiles, and they just don't know how to handle it, because these are foreign opcodes they can't understand. These flags go high, and now we force the processor to reset before it can actually try and run the malware. And so as you can see, the attack has technically been performed here with the screen blinking, but you'll notice that it recovers in just a second. There we go. So the image has come back online. And as you'll notice now, our recovery mechanism went back through the program memory and went ahead and cycled out the bad opcodes for a copy of the known opcodes. Now this copy in the recovery mechanism cannot be read by the processors and cannot be attacked by the attack vector. It's completely quarantined from the rest of the system. And so because we're able to bring back in those opcodes, we refresh the entire system with good program memory once again, and we go ahead and let it continue out of reset. And so as you can see, we're gathering live data again. There we go. As you can see here, this is where we went ahead and we started again, those specific opcodes that Tristan zoomed in here. Now Tristan's going to just send over 1 byte, which will go ahead and just change the screen mode. So this is the intended functionality, no longer an attack. And as you can see down here, the image refreshes over to edge detection mode. All right, let me switch back to the slides real fast. Here we go. All right. So yeah, that's the demonstration of our Cyber Shield kind of at work. The main concept here being that with the input data coming in and an output of some result, it is expected that a malware attack would be visible on the system. Like we'd be able to physically see where it happened and then analyze it with our tools. And so through this, we were able to demonstrate that by obscuring the opcodes in a heterogeneous system, we can not only detect when a malware attack occurs by seeing familiar opcodes across 4 systems, but we can also mitigate it by reporting the system. So with that, thank you very much for your time. I hope you found this informative and interesting, and I will be down for questions if you have any.
Questions for Dr. Major? Andrew, you look like you have. What did you learn?
If you learned how to attack a RISC-V, I won't be insulted. That's kind of the point.
James, what did you learn?
Attack something that work.
All right. Some of the Montana State people.
I learned how to look into FPGAs. I
Okay.
didn't actually know that they were a thing. Very interesting.
Did you hear that, Chris?
Yep.
Okay.
I don't have too much time to quite nerd out about FPGAs, but they're incredibly powerful. A lot of computational, like a lot of computing mechanisms kind of assume the hardware is fixed. But once you can create a system where the hardware can be changed dynamically, a lot more becomes possible. And not just cybersecurity, you can do machine learning stuff, hardware acceleration, just goes on, but I don't have time for that, unfortunately.
Yeah, I actually have a question. So there are 4 cores, or like something like that. And when one is running malware, then it won't communicate to malware to the other 3. But what happens to that one that was running malware? Is it then shut off, or is it like salvaged and brought back after like eradicating?
Yeah, the malware affected core is salvaged. I don't think I explained that too well in the video segment, but one of the RADPC recovery mechanisms that we brought into the project allows us to go back through the memory and fix all the bad values by comparing them with a copy. So that 4th core is salvaged and basically brought back to reset, so that way you can catch up with the other cores and the whole system keeps running.
And is there something you can do to like base off that data and like the change and the pretty much like the way that the malware was, I guess, like attracted to the system? Is there a way that you can then like defend it afterwards? And
Sorry, can you repeat that? His audio got a little weird.
Sorry. So like the other cores, once that core has been salvaged, is there certain data that you can collect as to why that core may have corrupted?
Yeah, that doesn't currently exist in the system as of now, but we have considered that for future work as more of like a diagnosis element to the recovery mechanism. So we can detect whether or not the instruction value was actually changed to a instruction range within data memory. So we could use it as a way of saying, oh, okay, this was a buffer overflow. We could add mechanisms to try and see if we actually saw a NOP sled. But yeah, diagnosis is one thing we have been considering a lot for future research. I think it would have been a little too much for Tristan with his defense at the moment. But overall, yeah, there's a lot of room to try and add more features that would be able to figure out what sort of attack we just endured.
Hey,
Jack?
Oh yeah, I was just going to ask, so I know FPGAs have been available for a few years now, and I've programmed one before. And so I was just wondering, are they starting to become more popular, or how abundant are they in society?
Well, yeah, that's a good question. I guess within like general public consciousness, FPGAs are certainly not quite there, not in the level of say like an Arduino or a Raspberry Pi. I have to explain FPGAs at every family reunion when people ask what I do for a living. It's kind of obnoxious. But within embedded systems design, FPGAs have definitely become a lot more popular, especially with a lot of supply chaining issues revolving around ASICs. And on top of that, big companies such as Intel and Intel and AMD have been eyeing FPGAs for a while. So Intel bought Altera, I think, back in 2016, 2017, and AMD recently acquired Xilinx. So they see a lot of potential in trying to leverage reconfigurable hardware, with cybersecurity being one of the main concerns. So I guess the short answer is, yeah, they're becoming more popular, but like in certain circles.
Thank you.
All right, any other questions? So thank you very much, Chris, for taking the time to share with us and all of your important research. Very insightful. So,
Anytime, I appreciate it. Thanks for having me.